This one I'm showing you is the FICE, Family Income and Expenditure Survey results for year 2018. Okay, so I would like you to be familiar with this figure so that you also understand the statistics, no, as related to the Philippine context. Okay, so as you can see, no, the average annual family income. Okay, this is from a survey, a sample, no, of I think 170,000 families, 170,000 households. So as we can see from the numbers, on the average, no, the annual average family income for the Philippines is 313,348 pesos. So if you were to divide that by 12, that means that the monthly average family income is 26,112. Okay? So it's not very high, no? So that just shows that the Philippines is indeed still a developing country, no? But what is good about this, if you were to look at the average annual family expenditure, okay, so it is this number, no, divided by 12, the expenditure per month is 19,887. So this shows that even if we are a developing country and that no, on the average, on the average, no, a Philippine household is not really that well off. Still, there is savings, so there is savings involved, as can be seen from the income and the expenditure, no? So there is savings. And then this is the standard error. I will be discussing that in a while. This is the coefficient of variation, and this is the lower and upper confidence interval at 95%. So I will be discussing how not these figures, no, but how to get a 95% confidence interval. So also for expenditure, no, the expenditure lies, we are 95% confident that average family expenditure lies between 235,927 and 241,355. If we were to look at the coefficient of variations, no, coefficient of variation is just computed by standard deviation over the mean. Okay, the bigger, no, if coefficient of variation is greater than 1 or greater than or equal to 1, that means that there is a lot of variability in the data set. But if it is less than 1, that means there is not as much variability in the data set. So let us look at these items here, no? So percentage to total expenditure, of course, we would expect that food would be the number one item, no, that would consume a family's budget at the level of 42%. Okay, but the 95% confidence interval, okay, for food lies between 42.23% and 42.87%. Now note this coefficient of variation. It is only 0.39. That means there is not so much variability with respect to food as far as the Philippine population is concerned. But look at this. So where is it really variable? Okay. Look at this. Anything that's greater than or equal to 1. Okay, recreation. Recreation is greater than 1. So there is a lot of variability in terms of recreation and culture. And we would, of course, expect that, no? Because while, okay, on the average, a household earns 26,000, but of course, we know that a month, no? But of course, we know that there are families who earn, who belong to the A class, no, in the socioeconomic classifications, and they of course earn like 1 million, 2 million, 3 million, 10 million a month. Now, contrast that to the recreation that, let's say, lower middle or lower income family would be able to do. Of course, it's wide, no? The ones who are rich would, of course, go abroad, no, for the holidays, unlike those that are just earning small incomes. So we would expect that recreation is, of course, very variable. Another thing that is very variable is education. Okay, that is again to be expected because while I would expect many of our families would be putting their children in public schools because of the free education, but of course there are there are schools with very high tuition, and I would think that those in the class A and B, of the socioeconomic strata would be putting their children in those very expensive schools. Okay, so that is how you think about coefficient of variation. When it's less than 1, the data is not so variable, such as food, for example, because food is a necessity. But if it's greater than 1, then it would be more variable, and that would and when you think of items, in the fives, that would be variable. We already talked about education and recreation. Okay, so let's start. Okay, so from sample to population, this is our sample. Okay, and this is the population that we're interested in. Remember, I told you in the first session that the meat of statistics is inferential statistics. Okay, this is the meat of stat, and the reason for that is because most studies really want to say something about the population, but it's just that because of time and money constraints, we have to contend with the sample. But of course, we want that this estimate X bar, which is the sample mean, is as close as possible to the population mean. That is our hope. Some people, they use what is called the point estimate of mu. Okay, and X bar is the point estimate of mu. Furthermore, X bar is an unbiased estimator of mu. Okay, so this is what we use in the sample when we want to say something about the population mean. What is an example of that? For example, we want to know, let's say, the average height of a Filipina. So we can get a sample of so many Filipinas, get their average height. That is this. So let's say we get an average of 1,000 Filipinas. So what is our sample mean? That is just the sum of their heights over 1,000. And it is our hope that this figure will not be too far from the average height of all Filipinas in our country. But of course, we know that it is unlikely that X bar estimates the population mean exactly. So some people prefer what is called an interval estimate instead of a point estimate. Instead of saying, okay, I from my sample, I found out that the average height of a Filipina is 5 feet. But you're not attaching any degree of confidence to what you're saying. You don't know how far it is from the real average height of all Filipinas. You don't know that. At least when you talk about an interval estimate, you're able to say that I am 95% confident, okay, that the average height of a Filipina is between 4'11" and 5'2". Okay, as you can see, I am not talking about a specific height, unlike that of the point estimate. I am talking about an interval, but at least I can say I am 95% confident that the true height of the Filipina, the average height, the true average height of a Filipina lies between this and this. Okay, so this one, which is usually 90%, 95%, and 99%, this is what we call our degree of confidence. Okay, this one, in this case, 411, that is what we call our lower confidence limit. And 5.2 is what we call our upper confidence limit. Okay, and mu is our parameter. Okay, this is what we want to say something about, our population parameter. Now, theta refers to any population parameter we might be interested in, not necessarily the population mean. We might be interested in the population proportion. We might be interested in the difference of two means. We might be interested in the difference of two proportions. Okay, so these are just a sample of some parameters we might be interested in. Note that a parameter is a numerical characteristic of a population. Okay, so how do we arrive at this? And specifically for the population mean, how do we arrive at this? Okay, first of all, remember this, okay? To establish confidence intervals, you must select from a normal population, okay? Now, if the population is not normal and the sample size is small, okay, we cannot expect our degree of confidence to be accurate. So while we say we're 95% confident that the population mean lies between these two values, we are not very confident about that if the population we are getting the sample from is not normal and our sample size is small. But even if we do not know the shape of the population, okay, as long as our sample size is greater than or equal to 30, okay, we can have good results. Okay, so again, when you get the sample so that you can, to be able to get confidence intervals, you have a normal population and you have non-normal population. If you have a normal population, there is no problem. Okay, you will surely get accurate results. But if your population is not normal, be sure that your sample size is at least 30 so that you will have good enough results. Okay, so how do we get the confidence interval? Okay, we must start with this drawing. Okay, this is what is called the confidence interval. Okay, this is what is called the confidence interval, the sampling distribution of the mean. Okay, this is called the sampling distribution of the mean. Note that the different values here, okay, in this axis are not xi, they are x bar. They are x bar. Okay, so what does that mean? If you were to get different samples, okay, so you have a population, no? You have a population, okay, and you want to get, let's say, you want to know the average height of a Filipina. You can get different samples, right? Let's say of size 30. You can get this one, you can get this one, you can get many, okay? And each one of this will have, of course, its own sample mean. Okay, so from this particular sample, you will get this particular sample mean. From this sample, you will get this one. From this sample, you will get this one, and so on and so forth. Okay, now if you were to plot this, no, the x bar 1, x bar 2, x bar 3, etc., they will form something that approximates a normal curve as long as n is greater than or equal to 30, regardless of how the original population looks like. Okay? Now, the mean of this distribution is mu. And the standard deviation is not sigma anymore. Okay? Because now because this is the sampling distribution of the mean. The standard deviation now of this distribution is given as sigma over the square root of n. Okay? Now, in real life, if we were really looking for the average height of a Filipina, will we get many of this? Will we get a sample again and again and again? No. We will just get one sample. Okay, we will just get one sample in real life. But just to show you, no, that this is what the theory says, that if you were to get many samples from your population, it will form something that resembles the normal curve as long as n is greater than or equal to 30. Okay, remember that, regardless of how the population looks like. Okay, so let's start with this. So we know already the sampling distribution, that it is approximately normal, no? So this is how it looks like, no? So this is mu. And then I said the standard deviation is sigma over the square root of n. So note this one. Okay. Some of you might wonder, no? Why this looks different. When you are doing just the simple normal distribution and getting areas of the curve, okay, the z there is defined as x minus mu over sigma. Why? Because you are just concerned about the area to the left or to the right of x, which is a value of your variable. Okay? So in this case, no, let's say you're talking about the ml content of a glass that comes out of the dispensing machine, no, of a soft drink dispensing machine. And you want to know, let's say the mu is 240, and you want to know what percent of glasses from this vending machine will have ml content greater than or equal to 250. Okay? Then this is your z. This is how z is represented. But this is not what we are doing today. Okay? We are getting the confidence interval of the population mean. And we had to start with the sampling distribution of x bar. Okay? And because we are dealing with the sample distribution of x bar, okay, we note that the mean is still the same, it's still mu, but the standard deviation is now different. It is not sigma anymore, it is sigma over the square root of n. Therefore, when you define your z, it is x bar. This is now the variable you want, not x anymore, minus its mean, which is still mu, over its standard deviation, which is sigma over the square root of n. Okay, so this is now your z statistic. So if we define two z's here, okay, this one is z sub alpha over 2, and this is negative z sub alpha over 2. Note that when you are talking about confidence intervals, what this means is what is that z value that has an area of alpha over 2 to its right. That is what it means. Okay? What is that z value that has an area of alpha over 2 to its right? So we can form this equality. The probability that z lies between negative z alpha over 2 and z alpha over 2 is 1 minus alpha. Why? Because if this is alpha over 2, no, this one here is of course also alpha over 2, because the z curve is symmetrical And the area to the right of the mean is the mirror image of the area to the left of the mean. So if these two are the same, imagine this is 1.95 and this is negative 1.95, you can be sure that the area to the right of 1.95 is equal to the area to the left of negative 1.95 because they are mirror images of each other. So we can form this statement, no? So what is the area here? What is the area here? If this is say sorry, this is 1.96. So if this is 0.025, let's say, and this is 0.025, what is the area now of this blue region? Good. 0.95. Okay, 0.95. So this is 0.95. So that is how it looks, no? See, this is 1 minus 0.05, which makes 0.95. And then after rearranging terms, because what we want is mu to be in the middle, because we want a confidence interval for mu, we will get this one in the green box. Okay, so mu lies between this and this quantity. Okay, that is the confidence interval of mu. Note that in a population, okay, and so you already know the standard deviation of that population, no? You already know sigma, and you already decided on what your sample size is going to be. Note that what determines the length of the confidence interval is just this. Okay, and z depends on what level of confidence you want to have. Is it 99%? Is it 95%? Is it 90%? Okay, because all the rest are already fixed. Okay. So what does it mean to be 90% confident? Okay, what does it mean to be 90% confident, for example? Okay, this is a very important diagram. This is the parameter you want to estimate, mu, no? You want to get the average height of the Filipina in the Philippines, no? To be 90% confident, this is what it means. Out of 10 possible confidence intervals you can create, no, you can construct, one of them will not contain the true value of mu. Okay, so if we look at this, no, if we look at this first one, this is x bar, no, this is x bar, this is x bar plus z alpha over 2 sigma over the square root of n, that is your upper confidence limit, and here is x bar minus z alpha over 2 sigma over the square root of n. That is how your confidence interval looks like. Now, is mu contained in this interval? Yes. Okay, this straight line here is mu. Yes, mu is contained in this interval. Of course, x bar does not capture mu exactly. There is this much of an error. Okay, but at least when you say, kunwari, when you say, for example, let's say the real average height of a Filipino is, let's say, 5 feet. So when you say, I am 90% confident that mu is between, let's say, 4'11 and 5'1, you are correct, because 5 feet lies in this interval. Okay, and so with this, no? This is the true value of mu. This is your x bar. This is your error. Okay, so you did not, no, when you got your x bar, it is not exactly the equal to the value of the parameter, but at least it is within your upper and your lower confidence interval. And so with the 9, but not with this. As you can see, this particular interval does not contain mu. Now, is it possible that in real life, the sample that you got from the population is this? Yes. So, will you say, oh, I'm 90% confident that this confidence interval I got contains the true value of the average height of a Filipino? Will you bet your life on it? You should not. No? Because for all you know, this is the one you got. But is it likely that this is the one you got? No, it's not. Because 9 out of 10 of the confidence intervals will contain mu, but 1 out of 10 will not. Okay? So remember that. That is what it means to be 90% confident. There is 1 out of 10 that will not contain the real value of mu in its lower and upper limit. Okay? But it is unlikely that that is what you get because you're working with the odds. No? 9 out of 10 favor you. No? That you would have gotten one of these 9 that would contain the true mu. Okay. So let us try to do this problem because there is something I want to point out. No? So let's solve this. So the mean and standard deviation for the quality grade point average of a random sample of 36 college seniors are calculated to be 2.6 and 3.3 respectively. Okay, so find the 95% confidence interval for the mean of the entire senior class. This is your objective. Okay, your goal is to find mu, which is the average of the population. And what is your population? Your population is the entire senior class. This is what you want to know, the average of the entire senior class. Okay, okay, so let's do this. What is given? Okay, the mean and standard deviation of 36, so sample size is 36. Now, the mean is 2.6. Now, some students have a hard time here, no? The question is, what is 0.3? Let's read it again. The mean and standard deviation for the quality grade point average of a random sample of 36 college seniors is 2.6 and 0.3. So this one is S. This is the sample standard deviation. That is not sigma. Okay? Why? Because it was taken from a sample of 36 students. Okay? So be very careful. So how does our confidence interval look like? So mu greater than x bar minus z alpha over 2. This was the formula, right? Okay, so we know that. Okay, we know that. But we don't know this. Okay, but it says we want to be 95% confident. So 1 minus alpha is 0.95. Alpha is 0.05. Alpha over 2 is 0.025. And if we were to look at the normal table, okay, the standard normal table, Z with an area of 0.025 to its right is 1.96. Okay, so solving this, oh, by the way, and then, but you're like, but sigma was not given. Okay, it's not given in the problem. There's no problem. Okay, you can substitute sigma with S as long as N is greater than or equal to 30. Okay? So, and that will not affect the accuracy of your results. Substituting sigma with S, as long as n is greater than or equal to 30, will not affect the accuracy of your results. Okay? So, putting everything inside, we get mu is greater than 2.5, less than 2.7. Okay. How do we interpret this? We say we are 95% confident, okay, that the average grade point, or the grade point average, the grade point average, now this is very important, of the entire senior class lies between 2.5 and 2.7. Okay? So, whenever you conclude, don't forget three things. Your level of confidence at 95%. Note that the parameter, okay, that is here in the middle is the average, okay? And finally, this is a confidence interval for the entire senior class, okay? Not of the sample. So again, the reason we do this entire process is because we want to know the grade point average of the entire senior class. And how will we know that? By getting a sample, okay, or in this case of size 36. And then we can finally use those data to be able to arrive at this confidence interval. Okay, now, what if I want a confidence interval that is 99%? What if I want the confidence interval for 99%? So everything is the same. Everything is the same, except this time, I want to be 99% confident. Will your confidence interval be wider or narrower? If you want to be 99% confident, wider or narrower from the one a while ago? Okay, so here we computed that we are 95% confident that the population mean, the average grade point, the grade point average lies between 2.5 and 2.7 to be 95% confident. Now, if I want to be 99% confident, is it wider or is it narrower than this? Okay, so from those I see in the chat, wider. Very good. Okay, let me make this bigger again. Okay, and in fact, if we do the entire process, we will get 2.47 and 2.73, okay, which is wider than what we computed a while ago to be 2.5 and 2.7. Are we happier with this? Are we happier when our level of confidence is higher? Okay, what if I want to be 100% confident? Okay, and I tell you, let's say I'm talking again about the average height of the Filipina. I say I am 100% confident that the average height of an adult Filipina will lie between 1 foot and let's say 10 feet. But I am 100% confident that this is what is gonna happen. Okay? You see, there is a balance between how confident you want to be and whether the interval you get is useless or not. In this case, this kind of statement that you're 100% confident that it lies between 1 foot and 10 feet is totally useless. Okay? So You may rely on a narrower confidence interval. Okay, but it is more useful to you than something that is so wide, even if you are 100% confident. Okay, because some of you might be wondering, why not 100% all the time? Okay, because you come up with uh, an interval that is so wide and might be useless to you. Or then you say, why not make it very, very narrow, like 80% confident, diba? Or what happens naman when you're 80% confident? Note that when you're 80% confident, 8 out of 10 of the confidence intervals will contain the true parameter value, but 2 will not. So you are now increasing your chances of getting an interval, that will not contain the population parameter at all. Okay? So you have to strike that balance, between what you want in your research. Okay. Now, for my okay, I think I can end here, but there's one thing I want to discuss. Okay, in the confidence interval for the difference of two means. Okay, what is an example of this? Let's say you have two schools. So this is school A and this is school B. Okay, and you want to enroll your son, but it depends which of these two schools have better has better reading ability as far as the grade 1 students are concerned. Okay, so what you can do is, okay, this is the grade 1 population, this is the grade 1 population. You get a random sample. Okay, you get a random sample here, you get a random sample here. Let's say 35 students here, let's say 30 students. Okay, give them the same exam reading test, and then develop the confidence interval. So this is what you call the difference, the confidence interval for the difference of two means. So if, let's say, this was positive 8, let's start with positive 8 first. And this is school A and this is school B. Okay, and they're both positive. So you can say, I am 95% confident that the reading ability of the grade 1 students, the average reading skill of the grade 1 students in school A is higher, is better. Okay, because they are both positive. That means this was the bigger quantity. They got in the sample, of the sample of 35, in the sample of 35 grade 1 students, they got the higher average score in the reading test. Okay, that's why they're both positive. But what if one is negative? Okay. Be very careful here. When you have a confidence interval, you don't know which of these numbers are correct. Is the difference -8? Is it -7? Is it -6? Is it 8, 9, 10? You don't know. You're just saying, I am 95% confident that the difference lies between these two. But note, between -8 and 10 is 0. Okay? For all you know, this was the correct difference between the two scores. So, when you have a confidence interval of a difference of two means, and you have a negative number on one end and a positive number on one end, meaning 0 lies in the interval, your conclusion is there is no significant difference. Okay, in the reading ability of the two schools, because it is possible that the difference of their of the scores, no, the difference in the average of the scores of both schools was 0. Okay, so be very careful when you have a conclusion that looks like this. It's okay. So thank you. I don't know if they want me to still talk about proportion, or we want to go to the question answer already.
Is it possible, from Angelo Cabik, is it possible to be 100% confident?
No, well, actually, the only story, no, that I was just really just stretching terms. You are only 100% sure if you do a census, no, meaning you must have studied the population. Yeah, I was just stretching the. In my lecture, I was just saying that sometimes, even if you want to be like almost 100% confident, sometimes it's useless because the interval will be just too wide for it to be useful for you. So the very common ones are really 90, 95, and 99%.
Those
But
are the standard
those
ones,
are the usual.
the
Yeah. No,
useful
but
ones.
yeah, but again, no, to be 100% confident, you must study the population. That is the only way.
How about 99.99%?
No, I've
Is
never
that
seen that.
possible? I've
In all
never
my
seen that.
Yeah, in all my readings, I have never seen 99.99.
Okay. So mga kasama, if you have more questions po, kindly type it in the chat box so para po ma-address natin. So, baka naman, Doc Leia, do you have a question for them?
Oh.
Maybe
Well,
they're still dazed with the discussion.
yeah.
So,
May I just reiterate the important points, no? So,
okay.
uh, here, there's a question here.
There's a question now. So, from Ziatrix Blasco, good afternoon po. May I just ask po kung papaano po natin kukunin ang number of sample in a population? Like if may fixed number po ba kukunin na sample sa isang population, or we can just get any sample that we want?
Okay, depending on, there are so many ways to get a sample size, but I can discuss with you. In the case of the mean, no, if we're talking about the confidence interval of the mean, I can discuss with you the size of the sample to estimate mu. Okay, so let me show you my camera again. So a while ago, I showed you this, no, in the let me just go back to the page here. Diba? This is the confidence interval for the mean. This one. Okay. So if you want to get a sample, if you want to get the sample size for estimating mu, it also just comes from here. Okay. So we can be 1 minus alpha 100% confident that the error, okay, because what is the error? This is your error. This is your error. This is the size of your error. Okay, because I should have explained this. Okay, in this drawing, no, I said the distance between mu, no, I said this black line here is mu, and this is your sample mean. This is your error. Okay, but we can say that the error will never go beyond this distance. Okay, it will never, it may lie, mu can lie anywhere here or anywhere here, but it will never go beyond this 2. So what is the size of your error? The size of your error is z alpha over 2 sigma over the square root of n. Okay, that is the maximum error that you can get. No, when you think of the mu and x bar as its estimator. Okay, so we will just have to solve for n here. So put the square root of n here. So that's z alpha over 2 sigma over e. And then just get the square of both sides to release n from the square root sign. So n is z squared alpha over 2 sigma squared over error squared. Okay, so this is one formula for getting sample size. And in particular, this is the sample size for when you want to estimate the population mean. But there are many other formulas that are available to you aside from this. But at least this one, it's very easy to think of, no? Because uh, it comes from knowing that the confidence interval looks like this, and that this one is the maximum error that can occur. So from here, just compute for n. I hope I was able to answer that question.
Okay. So there are a few more questions. Let's go to the next. The next question is came from Abby Ramos. Good afternoon. Is it possible to tell if a population is normal? If
Okay,
yes, how?
okay. So if the numbers are usually no, according to theory, for example, height, grades, IQs are usually normally distributed. But if you have a set of data that is manageable, no, the very first test is to draw the histogram. So that's number one. If the histogram looks normal or approximately normal, then you can assume the distribution is normal. Number two, you can use the empirical rule. Once you draw the histogram, no, and it looks approximately normal, you can test. Do 68% of the data really fall within plus minus one standard deviation? Do 95% of the data really fall between plus minus two standard deviation? And do 99.7% really fall within plus minus three standard deviations? Okay, so that's rule number two. And then there is such a thing as a normality plot. There is a normality test in SPSS as well. Okay, so test for normality of the data before you use confidence intervals. Okay, as I mentioned before, unless so you're sure your data your results will be accurate. But if in case your population is not normal, remember, just make sure that your sample size is greater than or equal to 30 to have good results. What are those? Those are the two initial tests: the histogram and the empirical rule.
Okay. So next question came from Armando Corpus. Ma'am, ma'am, example may 20 groups po kung saan kukuha po tayo ng random sample. Is it better po ba na equal number of sample ang kukunin per group para sa mas ma-confident ma-confidence result?
Okay. In reality, I mentioned a while ago, Armando, in reality, you will naman only really get just one sample. Okay? The reason I showed the sampling theory and the sampling distribution, no, is because in theory, if you were to get many samples of the same sample size, and then you will have a sampling distribution that is approximately normal as long as n is greater than or equal to 30. But in real life, you will really just get one sample.
Okay. So do we still have the can you still answer one more question?
Yes, yes.
Okay. So the next question came from Manolita Ramos Oligo. How many cases are needed for an extrapolation?
Cases of what are we talking about? Again, Manolita, I don't know if I'm answering this correctly, no. But again, um, as long as it's from a normal distribution, no, you can get a confidence. You can construct a confidence interval. But if you're not sure, no, if the population is normal or not, make sure that your sample size is greater than or equal to 30.
Okay. So a question
Um,
just came in. This came from Nancy May Bation Omandam. Good afternoon. May I ask as to how can a quasi experimental research be done in terms of sampling?
oh no, I'm sorry, I'm not able to answer that uh, based on my report. I will have to study for that answer
Okay.
to answer that.
Okay. So I guess that wraps up our question and answer. Actually, thank you, Leah, Doc Leah, for sharing your time and knowledge to the Kasama community.